Good morning, good people. It is me again. At 5:22 in the morning, recording my first video for the day. All right. Now, this is where we stopped yesterday, or in the last video rather, and we have to look at an important experiment. The experiment is the Young's double slit experiment. So, a fella whose title is obviously Young decided to perform Young''S double slit experiment. Young decided to perform a simple experiment. I use the word simple very loosely. Young got a lamp, and then he decided he was going to use this lamp in a very intelligent way to produce or to make two sources of light. So he got a screen, some material that didn't allow, made of some material that didn't allow light to pass through, and he put up one hole in it. Then he got a second piece of material that didn't allow light to pass through, and he put two holes in it. And then he got a final screen or piece of material to allow the light to shine on and create a pattern. So light from this source traveled in this direction, hit the first screen with the first slit, and it diffracted, it spread, and it hit the second screen. When it hit the second screen, it hit the two holes in the second screen and it spread. Now, what happened was the two holes acted as two sources of light. Two sources of light. And there was an area or a region in which they overlapped. We could call this the display screen. In this area of overlap, interference occurred. FERENCEOCCU. My English teacher, my primary school teacher, would have a fit if she saw my handwriting. Occurred here, right? So interference occurred here, and an interference pattern was generated. So here's what the interference pattern would look like. You see, there would be points or spots that would be very bright, very, very bright, and it would look as if light from, let me use the two colors, that might make it more effective. And those spots looked as if light from the two sources, I shouldn't say the light from the two sources, the easiest way to explain it, it looked twice as bright. And what happened in those places was constructive interference occurred. And then there were spots on the screen that were dark, as if no light was shining there. And in those spots, destructive interference occurred. If you remember my very, very brief explanation of interference, if you think of it this way, if you think of a wave traveling like this, and then over that or to that, I shouldn't say over that, that's not proper, but let's say it runs into a second wave, second similar wave, and the two waves meet like this, what they end up producing is a new wave that is much, much larger. Alright, the amplitude of the wave is much larger. In the case of sound, the wave is louder, and in the case of light, the wave is brighter. So These are your dark spots. Dark spots. And this is from destructive interference. Because you can have, like my diagram shows, my fancy yellow and blue graph shows, you can have two waves meeting and you get a bigger wave, right? That's constructive interference. But two waves can also meet in such a way or interact in such a way that they cancel each other out. And you get basically no wave. You just get a flat line. This is constructive interference, and this is destructive interference. So the dark spots were from destructive, and the bright spots were from constructive interference. Constructive. Simple way to remember it. Constructing is building, is, destructive is breaking down. Easiest way to remember it. Now, an interesting thing happened as well. In this area, interference did occur. But if you think about it, the regions here, yeah, let me use this color. Actually, no, use this. In the middle, right in the middle of this region of interference, you would have the brightest possible interference pattern being produced. But when you move away from this very bright spot, it gets less and less noticeable. Why? If you look here, this is light from one source only, and this is light from the other source. Let's call this, light from source 1, the green source, and this is light from source 2, the pink, purple, whatever color that is, source. So the further you go from the middle of the interference pattern, or as you move from the middle of the interference pattern, the interference becomes less and less obvious or noticeable or observable, because you're moving from the area where the two sources meet to an area where you have more of one source and less of the other. That is all that happens. So if I'm drawing it on my fancy interference pattern, it would be very bright. Oh, I need a brighter color. It would be very bright right down the middle here. But as you move that way, it gets darker. Well, I shouldn't say darker, less noticeable. And as you move this way, it gets less noticeable. And this is Young's double slit experiment. This experiment was very, very important. You might be thinking, sir, everything important? Yeah, everything is important. The reason this experiment is important is because it helped or provided evidence for the nature of light. So, historically speaking, there has been debate over the nature of light. The nature, N-A-T-U-R-E, of L-I-G-H-T, the nature of light. So, light clearly is a wave, right? It's a wave. How do we know this? Well, we have reflection. It reflects. It refracts. It diffracts. And it interferes. No. Who proved this? This was Snell. This diffraction, there was a Dutch fella, I will not pronounce his name, but he did some incredible work on diffraction. And then, of course, we have Mr. Young. These were the people whose work helped prove these things. Now, on the other side of the fence, we have other folk who believe light is different. They believe light is actually made up of particles. These particles are called photons. Now, Photons. They believe light is a stream of photons. The first person to propose this was Newton. And he proposed that light was made up of packets of energy, right? Crazy as it sounds. Light was made up of packets, I believe. I could be wrong. It is early in the morning and my brain probably is not fully loaded, but this is what he believed. Then came Uncle Albert, good old Einstein, and Einstein proved Newton right. It is called the photoelectric effect. Now, the photoelectric effect proved what Newton said. So here we have two sets of evidence, which we cannot deny. One set is not right, the other set is not wrong. Both are correct because these experiments have been repeated without for years. I was about to say centuries, but yeah, it's about, yeah, give or take, centuries. And everybody gets the same results. They're accepted as clearly being real, genuine, true, and honest events. So then, what is light? Well, you see, light is both a wave and a stream of particles. So we say light has a dual nature. It is both wave and particle, and we call this wave hyphen particle duality. And that is the nature of light. Now, the next thing we have to look at be lenses. Lenses. There are two types of lenses. You have your converging lenses are your convex lenses. These are lenses that are shaped like the lens in a magnifying glass. These focus light. This is a single and this is a double. These lenses that focus light are called convex lenses. On the other hand, you have your diverging lenses, diverging lenses. And these scatter light or spread it out. These look different. This is a double. This is a single. And we call these concave. Moving on. Now y'all are going to have to forgive me because my ability to draw straight lines, shucks, is not very good. So here we have a convex and a concave. Now, if I have a single straight line, right? Actually, I shouldn't say that. That's a poor statement. Light is assumed to travel on straight lines. A single thin sliver of light is called a ray of light. If I take several rays and put them together, I get a beam. So if I shine a beam of light through each of these lenses, I will get some interesting patterns. Again, these are just sketches, right? Nothing here is drawn to scale. My convex lens is going to focus the light, and my concave lens is going to do the opposite. So there are a couple points that are similar for each. There's this, and then there's that. I will call this 1, 1. This video is probably going to go over my little 20-minute limit. There's that. Then there is this. That's not well labeled, so So 1 is called the principal, Principal, the principal focus, or the focal point. For a converging lens, it's where light converges, and for a diverging lens, it is the point from which light appears to scatter. If you look at my green lens on the right, my diverging lens, I hope I said diverging before, but anyways, if you look at my diverging lens, it would appear as if the light is spreading from this point. Now, do note that for a converging lens or a convex lens, this point is real. It's an actual point that you can perceive, so to speak. But for a diverging lens, you can't perceive it. You can't like notice or observe that the light appears to be spreading from this point. When light is focused to a small point, you can observe it. It is observable. It is something that you can see, something that you can observe, something that you could take note of. Classic example: get a magnifying glass, go out in the sun at midday, and move the magnifying glass close to and away from the ground. When the ray of light, or when there's a dot, well, actually there's a point, you're going to see a circle. When that circle is at its smallest, a little circle, bright circle, when it's at its physical smallest, you have brought all the light passing through the lens to the focal point of that lens. When it's big and broad and large, the light is out of focus. So for a converging lens, you can easily detect the focal point. For a diverging lens, no, you can't. I should probably, my paranoia is strong. Let me use a different color. Let me use light blue. So 1 is the principal focus, Principal, focus, or focal point. is the principal axis. Now, the principal axis is the line along which, if a ray of light travels along that line, its path is not altered or changed. So any light traveling along the principal axis basically passes straight through the lens and just goes on its merry way. 3 is the focal distance. I said it and it sounds so weird now. It's like when you write a word and it looks like it's incorrect. Yeah, well, it's focal length. I said focal distance. Focal length, Length. And 4 is called the focal plane. Now, the focal plane is a two-dimensional plane. It's that I want to sneeze. Excuse me. Excuse me, sorry about that. I couldn't help it. As I was saying, the focal plane is the distance, not the distance, is a two-dimensional plane that exists through the focal point. Like it's a flat two-dimensional surface on which you would find the focal point, and it is parallel to the vertical axis of the lens. Right? That's all it is. Now the focal length is the distance from the vertical axis of the lens and the focal point. The focal length is the distance between the vertical axis of the lens, either lens, and the focal point. And this is basically lenses. There is one formula you need to know for lenses. We will look at lenses, magnification, real and virtual images, and we will be done with this section of the syllabus. Hurrah! Now, the formula is very simple, right? The formula is the lens formula. 1 upon f is equal to 1 upon u plus 1 upon v. Simple formula. Focal length of the lens. This is the image created by the lens, the image distance from the lens, and this is the object distance from the lens. The next formula is magnification. Magnification. Magnification is simply a ratio. It is, I think, common M, and it's image height over object height, object height, or image distance, we've seen this term before, V over object distance, U. Now, magnification is not a percentage. It is not. It's just a ratio of these terms to each other. Yes, images. So images can be one of two types, real or virtual. Real images can be projected onto a screen. ONTO, a screen, SCREEN. On the other hand, virtual only exist in the lens that causes them, well, that creates them. I said the lens. I should say a lens. A lens. And this is the difference between the two. Real images can be projected onto a screen, whatever the device. Virtual images, you can't project them. They only exist in the lens. Classic example of virtual images would be, I think, images in a magnifying glass. What you see in the magnifying glass, you can't do anything with it. You observe it, and that's it. Anyways, this is the end of Waves and Optics. It has been fun. However, I have to make the other videos on electricity and magnetism, and I'm going to start as soon as I finish this one. As always, like, subscribe, comment, and once again, thank you for the views, the support, and do share with your friends, especially at exam time. Walk in the corner, stay sane, stay safe, and I'll catch you in the next one. Bye bye.